Welcome to our second lesson of types of reactions. We're going to take a look today at the different acid and base theories. Now the theories that will be under discussion today is going to be that of Lewis, Arrhenius and Lowry-Bronsted. So each one of these defined an acid and a base differently, and we'll look in detail how these definitions and theories for the acids and bases would differ from each other. Now we're going to start off with Lewis acid and base theory. Now we have already discussed mostly what Lewis said about an acid and a base when we did our Lewis diagrams in the beginning of term 1. So just to refresh your memory again, when we're going to talk about a Lewis acid and base, we're going to refer to the dative covalent bond that formed. And it was also referred to as the coordinate bond. Now let's just briefly revise again what this dative covalent bond was on. We, for example, started with ammonia and would add to it a hydrogen ion. And this is from where our dative covalent bonding occurred. So I'm going to show you again in your Lewis diagrams how the ammonia and the hydrogen ion is going to end up bonding using the dative covalent bond, or otherwise known as the coordinate bond. Now remembering that your number of electrons found according to your Lewis diagram around the nitrogen would be equal to the number of valence electrons. And if you can remember what valence electrons was, those were the electrons found in the outermost energy level. And it corresponded to the specific group number in which the element fell. So for the case of nitrogen, it fell in group 5, which means it had 5 valence electrons. And we've placed 1 electron on each side, and then if we still need to add in more electrons, like we do in this case, we'll need 1 more, then the electrons would start pairing up. Now for the ammonia, we had 3 hydrogens, and our 3 hydrogens, which has only 1 electron in the outermost energy level, attached to each one of the unbonded electron pairs of the nitrogen. Now when we take a look at the hydrogen ion, remember though we said that our hydrogen would have had 1 electron in its valence shell. If it becomes an ion, it means that it has lost, in this case, the electron. And the charge that it will then have is a positive. So it has a positive charge because it lost that 1 electron. And you would have noted that in the previous cases, the hydrogen needed that electron to help bond to the nitrogen, because every bond must consist of 2 electrons. So now seeing that the hydrogen ion have no electrons to bond with, the ammonia though has still got this lone pair of electrons, which is a total of 2 electrons, and therefore can then go and bond to the hydrogen, so that between the 2 of them, the nitrogen is now going to donate its lone pair so that the hydrogen can accept it, and more specifically the hydrogen ion can accept it, and now form a bond between those 2. So that was the dative covalent bond. Now in this dative covalent bond, the whole molecule, which is now going to be ammonium, is going to take up this additional positive charge of the hydrogen ion. Now according to Lewis, he termed this hydrogen ion that accepted the lone pair as an Lewis acid. And the nitrogen of the ammonia, he's going to term the Lewis base because it donates a lone pair. So according to the Lewis acid and the Lewis base, it all has to do with the lone pair. So in the acid's case, it's going to accept the lone pair. In the base case, it's going to donate the lone pair. Now let's go and take a look at our Arrhenius theory. Now the Arrhenius theory was though limited to water solutions. He only referred to in his definition when an acid or a base dissolved in water. Now not many cases do the acids and base actually dissolve in water. They might even react with each other or not with water at all. And then Arrhenius theory would in this case not hold water, which means it would actually not apply. Now according to his theory, an acid would end up releasing hydrogen ions when dissolved in water. Let's take a look at a reaction. If you, for example, have hydrochloric acid, when it's going to be dissolved in water, and you'll see later on in our next lesson we're going to call it ionizing. It's going to break up basically into hydrogen ions and chloride ions the moment that it does dissolve in water. And then we would refer, according to Arrhenius, because this happens in water, that this will then form hydrogen ions if it was an acid. Now sometimes they actually do write the water in the reaction, and you'll have the hydrochloric acid plus the water, and then you would note that the hydrogen ion is going to combine with the water to form an hydronium ion, which we have spoken about before when we did the dative covalent bonding for it as well. So it has actually two names. It's either referred to as the hydronium ion or the oxonium ion, but both of them refers to the H3O plus ion that arises when water combines with the hydrogen ion released from an acid when dissolved in water. Now for a base, the definition according to Arrhenius will be that it would release hydroxide ions when dissolved in water. And let's take a look at our sodium hydroxide. Now obviously this is different though than it would have been for the acid. If my sodium hydroxide dissolves in water, it breaks up into sodium ions as well as hydroxide ions. Now specifically for bases, this is not always true because not all bases can dissolve in water. And that's how come Arrhenius theory had only a limited area, and that was only when dissolved in water. And we needed to go and look beyond reactions with water, how to go and identify an acid and a base. Now let's go and take a look at our Lowry-Bronsted theories and how he defined acids and bases. He said that acids are seen as proton donors and a base a proton acceptor. Now when they talk about protons here, they are not actually referring to the proton particles inside of your nucleus of the atom. Let's just quickly go and break down what does proton mean again and what they will be referring to when they talk about a proton. Now a proton, as you would know it, is going to be that particle, which we call a subatomic particle, found inside of the nucleus of an atom. Now if you can remember again, inside the nucleus of an atom we would find protons, which is called the positive particles, and neutrons, that is the neutral particles. If we're specifically going to refer to the hydrogen atom, then you would see according to the periodic table, it's got a proton number of 1. That means it's got only one positive particle found inside of the nucleus, and if this is a neutral atom, like all atoms are, then that means there will only be one electron, because that means only one negative will be needed to cancel out this positive to make it a neutral atom. If though this becomes a hydrogen ion, then it means it has lost an electron, as we've seen in our previous definition of the Lewis acids and bases. So that would mean our little electron that was here in the orbital is now removed, and the only thing that we've got left inside of this nucleus is basically the proton and the neutron. But because the neutron doesn't have any charge, that means that the atom becomes then positively charged. So this hydrogen ion is thus positively charged, and because it contains only one proton, which causes this positive charge, we will refer to a hydrogen ion, according to Lowry-Bronsted, as a proton. So if we tell you, Lowry-Bronsted said an acid is a proton donor, we meant he said a hydrogen ion donor. And if he said that the base was a proton acceptor, it means a hydrogen ion acceptor. Now let's go and apply this to a specific reaction. Now here we're going to have a reaction of hydrochloric acid combining with ammonia to form ammonium ions and chloride ions. Now remember, we need to go and look at which of these molecules donated a proton, and this proton is the hydrogen ion, and which one accepted this hydrogen ion. So we would see that my hydrochloric acid ended up becoming Cl-, which meant that it basically lost a hydrogen ion. So it donated the hydrogen ion, and my HCl, because it donated a hydrogen ion and ended up being Cl- without the hydrogen now, is going to be seen, according to the Lowry-Bronsted, as an acid. If we take a look now at the ammonia, it accepted this hydrogen ion coming from the hydrochloric acid and ended up forming our ammonium molecule. Because it gained an additional hydrogen, it becomes now NH4+. And remember that we'll gain this charge because we've gained the charge coming from the hydrogen ion. So because it accepted this hydrogen ion, it will be seen the ammonia as a base. So that's how we're going to define an acid and a base according to Lowry-Bronsted. Now, reactions where substances is going to react as proton donors or acceptors is going to be known as proteolytic reactions, or sometimes also referred to as proteolysis.